nanohub.org.
All right, so we'll get started again. This will be 2 lectures. Roughly a very fast overview of the NEMO3D tool. You sort of saw the power of the NEMO1D tool. Now we'll talk about NEMO3D as a sort of an infrastructure, what it can do. And in the second lecture, we'll talk about how we model single impurity systems in silicon and for quantum computing, those kind of things, how you apply NEMO3D to do million atom electronic structure calculations. All right, so in the previous lectures, I hope I had somewhat convinced you that if you are working at the nanometer scale, you can't really think of a Jellium model of material anymore. It's not like you can make things smaller and smaller, but really that the atoms, the discrete atoms in the system actually make a difference. So if you want to do simulations that include atom by atom, there's really 2 choices in a sense. If you want to do quantum mechanics, in this realm, you can do pseudopotentials or you can do local orbitals. And pseudopotentials are usually derived out of plane wave representations, and local orbitals, well, are just local orbitals that represent electronic structure. Now, the things I like to consider as an electrical engineer have a finite a finite extent, right? It's like a quantum dot or a nanowire. I don't look at infinite arrays in 3 dimensions of quantum dots, but I look at things that are finite and they have a contact on the left, contact on the right. They like to get electrons in and out, right? They're not periodic. So that's why I chose really a local orbital approach, because a plane wave approach is really only good for things that are infinitely periodic. And you should choose your basis state according to the problems you'd like to solve. Okay? Also, I'm interested in semiconductors that are stable, meaning there's no bonds flopping back and forth. I'm not interested in the chemistry of establishing those bonds. So I don't have to do ab initio calculations either that really establish the chemistry of a certain bond. So I'm allowed to throw away certain things that I'm not necessarily interested in. So also I want to do structures that are realistically large, say 20 nanometer type structures. They might contain 1 million atoms. So I should write something that is immediately parallel because I probably won't fit that onto a single computer. And I like to explore the whole design space. I like to really have a design tool that allows me to look at arbitrary materials and arbitrary configurations and geometries. All right, so the approach that we use is that we start from empirical tight binding, like this, where we have atomic orbitals at 0.2 nanometer size. We map them into realistic structures like quantum dots or carbon nanotubes that might contain millions of atoms, and we compute eigenstates of the system. So NEMO3D was begun in 1998, and there we realized we want to do atomistic representations of materials, but we can't possibly afford doing transport with that. So the only thing we could hope for at that time is compute eigenstates of the system. No transport, okay? So, a big problem was the parameterizations of these orbitals, and we really developed a generic framework with genetic algorithms that allowed us to fit these tight binding parameters, and so we can use them sort of as a material database and not mess with them anymore. We compute the mechanical strain in the system, and we developed parallel algorithms that were efficient to run on parallel computers. And about 3 years ago or so, when I was then already here at Purdue, we demonstrated scaling of this code to very large systems. In fact, we ran on 128 cores in parallel a system up to 50 million atoms. 50 million atoms may be pretty arbitrary to you, but that's roughly 100 by 100 by 100 nanometers. Okay? You can plop a modern field effect transistor into that and calculate the strain and the electronic structure of a system like that. Okay? That's pretty unique capability. And we use that for quantum dots, nanowires, quantum computing type things that will be highlighted in the next talk. The basis here is a tight binding basis where every atom is represented with s, p, and d orbitals. And they're literally mapped spatially and connected with each other with bonds. Okay? So there's the concept of bonds, the concept of crystal symmetry is built into the basis. Okay? And if you chop a bond, we will know about the dangling bond. If you put in another material, it's literally an atom-to-atom transition. Okay? The model is called a tight binding, and here's a sort of a zinc blended crystal that shows you the 4 nearest neighbors, and the 4 nearest neighbors are connected with little matrices that connect the s, p, d, and s orbitals on one atom to the equivalent orbitals on the other atom. You can write it down in a form like that, where you have on-site matrix elements and you have coupling matrix elements. And automatically you get these complex-looking dispersion curves. And so here you see gallium arsenide, and here you see indium arsenide, and in the dashed lines you see an sp3 model, sp3s star model, and in the solid line you see an sp3s star d5 model. So typically, when we work in indium arsenide, gallium arsenide these days, we use the sp3d model because it gets the excited states and the full Brion zone of the material quite nicely, also as a function of strain. So that's built into the model. Right? We don't stick that in anymore. Yes?
Is it possible to fit nanostructure, band structure instead of bulk?
Oh, so the question is it possible to fit nanostructure, band structure? So let me return that question to you. What does a nanostructure, band structure mean? It's not an infinitely periodic system anymore. Band structure only makes sense on a periodic structure.
So let's say a nanowire.
Yeah, so then the approach we take is we fit these material parameters once against bulk. And we do as good a job as we can, and we assume in the systems where we'd like to apply them, there is no bond changes, no rebalancing of charge, and then we model the nanostructure with this basis from bulk, which is a deep dive, right? You take a jump off a cliff and you hope it actually works. And if there's no bond redistribution, if there's no chemistry changes, it actually works quite well. And I'll show you examples of that later. All right. So we can do this with a system of 52 million atoms to give you an idea that this is a matrix of 10 to the 9 by 10 to the 9 in a basis like that. That is not something you particularly write down by hand or solve by hand. Okay? The bond lengths and bond distortions are included. So here's, say, an s orbital on the left coupled to a p orbital on the over here on the right. If we now change the bond angle or the bond distance, that is immediately comprehended in the model. Okay? So strain effects of distortions are immediately in the model. We don't stick it in after the fact or by a parameterization. So the flow of NEMO3D is like this. We have an input deck, and in the input deck, we stick in the algorithmic determinations, the geometry description, etc. Then we construct a 3D geometry, like a 3D representation of the atomic world. Then we do an atomistic relaxation. That means we consider these atoms like balls on a spring, and they can relax. Right? Because some materials like to be on a different lattice constant than others, and they sort of fight with each other and push left and push right, and we let them do that, like a classical system, and until they have sort of their equilibrium resting place. And then we lock them in place, and we can compute strain tensors, which we might use for piezoelectric potentials, that then feed in, and the atomic positions then feed into the Hamiltonian construction. That is sort of the Schrödinger equation, so to speak, in tight binding with the atom positions locked in place. And then we calculate the eigenstates of that Schrödinger equation, and we dump out data. Yes?
The atomic relaxation, is that like an electrostatic, like stable?
It's a so-called valence force field method, where basically what you do is you say atoms would like to stay at a certain distance, and if you push them out of the distance that they would like to be in, they gain some energy, right? But everybody gains some energy. It's sort of like a minimization problem where everybody naturally would like to lay at a certain distance from its neighbor, a particular neighbor, and the neighbor-neighbor interaction is different. For example, indium arsenide likes to be in a different bond length than gallium arsenide, but if you throw those guys together, they all argue with each other, no, I like to be here, and then you do a conjugate gradient minimization, and that is what this atomic relaxation does.
Is there potential for finding the wrong minimization?
There's potential for that, but if you really start out from a really bad starting point, I presume you can end up in the long one. But this is a roughly convex problem because everybody is sitting at a parabolic-like minimum. So you're close to something you can find reasonably well. It's not a crazy optimization. Yeah. So here's an example, right? So here you have maybe gallium arsenide and indium arsenide, and you try to put them together. They're going to have to adjust each other in its distance, right? Say you grow indium arsenide on top of gallium arsenide, and let's say you have a deep substrate here, right? You go deep, and basically the gallium arsenide said, I'm not moving. And you guys are just a few indium arsenide guys, right? You adjust to us, right? The choice they have is to roughly, by Poisson ratio, they roughly need to conserve volume, so they need to expand out a little bit. Okay? And that would automatically come out of this model. Okay? All right. So strain can impact this electronic structure. It deforms the crystal. The band edges are shifted. The degeneracies of the heavy hole and light holes are lifted. You can extract a variety of deformation potentials out of this model to follow the conduction band edges. So here, if you have a distortion of the tensor, the conduction band edge is just a function of the diagonal elements of the strain. And the valence band actually has two components, the hydrostatic and the biaxial distortions. And that's all really, in effect, built into the model. We don't stick it in. Here's a sort of a detail on how we do piezoelectric potentials. If you have strain, you actually have piezoelectric coefficients, and out of these strain coefficients, you can calculate piezoelectric charges that are sitting on the crystal. And with the charges, we can calculate a potential, and the potential we can then use back in the Hamiltonian. Okay? All right. So in the eigensolver, what we do there is we represent Schrödinger's equation in a large matrix. It's a Hermitian matrix, but it happens to be pretty large. And what is also bad or hard is we have to get to the interior eigenvalues. Normal eigenvalue solvers would like to converge the iterative ones on the extremal eigenvalues. To get to the interior ones is actually very hard. Interior into the spectrum, I mean. Right? We're interested in the conduction band edges and valence band edges, but there's states at minus 30 eV and plus 20 eV, right? There's a whole energy range. So actually to make that work is quite tedious. And we have that working, and it can work on a variety of clusters, and it can work in parallel. So the parallelism is like that. You take a chunk of semiconductor like this, and you take it into slices. Think of a bread, and you slice it. And since we really have only nearest neighbor interactions, we only need to communicate from one slice to the next only with the atoms that are on that slice. Right? So the beautiful thing about parallel computing is you have lots of sort of compute slaves that can do things, right? But if they need to talk a lot and need to exchange a lot of information, then they talk and don't work, right? And if you talk, you don't work. Unless you're a teacher, then you can talk and work. So, so there's communication across these interfaces, and you can sort of represent this Hamiltonian matrix into blocks like this, and only communicate over the blocks. And the mechanism we use to calculate eigenvalues in this structure is really by doing repeated matrix vector multiplies. Okay, that's basically part of this iterative solver. So we have a big Hermitian matrix, 10 to the 9 by 10 to the 9. We multiply it repeatedly with a vector, get a new vector out. We do some post-processing on that vector and repeat that. And that algorithm eventually gets us to the eigenvalues. Okay? Because you can't do a full eigenvalue solution, right, of a matrix of 10 to the 9 by 10 to the 9. Right? That's too many eigenvalues. You couldn't even store them. You couldn't invert the matrix, right? You have to have an iterative solver. All right, so we have a couple of solvers we use. We typically do a 2-pass Lanczos that we implemented. And the reason why we immediately went parallel in 1998, 97, when I was interviewing for my job at JPL, a person that my future boss told me, well, we are working a lot with supercomputers. And I said, supercomputers are utterly useless for engineers. And he said, yo, you might change your mind. We just built Beowulf computer number 2 in the world in our lab. That was basically a hunk of PCs sitting on a rack on a commodity network, but dedicated to computing. And the first one we had access to was called HiGlac. It had 16 Pentium Pros at 200 megahertz with 128 meg of RAM. And you're like, what is that? I have that on my laptop today. Well, the point was we didn't, and that was still a very cheap supercomputer, but it was available. And I could run over it days and nights and weekends, and I didn't have to talk to anybody for permission or queues. It was my private supercomputer. Okay? So that enabled us to do certain things. And it went through several generations, and really the supercomputing industry and the supercomputing labs actually looked at those things and said, like, what is this? This is not big iron. It's a hunk of PCs. Within 4 years, roughly, this turned the whole world of supercomputers around. I mean, if you buy a computer today, a supercomputer, it is basically a hunk of this, but packaged a little bit nicer. Okay? It completely changed the world of computing. And writing programs that actually can utilize that kind of compute power, it's not necessarily easy, but it's the right thing to do if you do computational science. If you build and design a code immediately, or only in mind, yeah, I'll put this on my little machine, right, and it runs in serial for 3 weeks, you're out of your mind, right? We have now computers and have access to that have 200,000 cores, right? 200,000 cores. So you got to write your software that actually can use that. Okay? So these are some early scaling results, and the glory game is really here. If you double the number of processes, you'd like to divide your compute time by 2, right? So you don't want to waste time. So in an ideal sense, these should be straight lines, and even early on, they were roughly straight lines. In 2007, we were running up to 8,000 cores on a Cray machine, right? Pretty much linear scaling, which is very nice. And the cool thing is that was code that was designed for 16 Pentium Pros. Okay? So if you design it well and know what you're doing, it can still, given the right problem size, scale to 8,000 cores. Okay? All right. Recently, we've been restructuring this NEMO3D code, and 2 students of mine basically rewrote it completely, and it instead of just slicing it in slices, they can now slice it in rods in 2 dimensions, or even in little cubes of 3 dimensions. They showed scaling up to 10,000 cores. The graph I showed you with scaling to 8,000 cores in NEMO3D is really a cheat, because it was a really, 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 really long nanowire that I could slice 8,000 times. Well, I'm not particularly interested in these really long and thin nanowires, right? If I really want to slice something 10,000 times, I got to slice it this way. Okay, so that was one of the achievements of 2 of my students, Suni and Hoon, that actually implemented code that scales like that. All right. So really the objective is to run a cubic-like simulation domain and run it to some 10,000 cores like that. And these machines are actually available, right? There's 3 machines in the US that have capabilities like that. There's one machine with 60,000 cores, one with 90,000, and one with 220,000. And we actually have access to them, and we run on those. All right. So, but one thing you want to do is sort of prove to yourself that you can actually get reasonable results with things like that. Okay? So let's assume we have a quantum dot like this, and we're interested in the interior eigenstates of this, like an s and a p orbital, they might be separated by as little as 10 milli-electron volt. But they exist in an eigenspectrum that spans about 40 electron volt, right? From the bottom of all the bands you have to the top of all the bands. And you want to isolate these few little guys in here and find them. So the numerical experiment, what we've done is we've taken a quantum dot and put a box around it and calculated, say, the S-like state and the PX and the PY-like state. Okay? We left the quantum dot the same size, but make the box that surrounds it bigger. Okay? Can we still find the states and find them at the right energy? And then we make the structure even bigger, like this, to 21 and then to 52 million atoms. We find the same states. Okay? So when you build an infrastructure like that, you can't just write the code and think you can run it. You got to really validate it and test it as well. So you got to build those validation and tests into your process. And then you got to document it, and then you have an audience that nods their heads. Oh, that's pretty cool. All right. So the point is we can get unique and targeted eigenstates of correct symmetry. Okay? It's not just arbitrary states, but it's the ones we really want and we understand. All right. So the bottom line is that we have this capability now that we can look for quantum dot-like systems, we can analyze valley splitting, we can look at alloy disorder, quantum dots, nanowires, single impurities, and in the next presentation, I'll give you an overview of what we can do with that. Okay? So, any questions on the general infrastructure? Yes?
So for atomistic relaxation,
yeah.
Do you minimize the energy of the system?
We minimize the total strain energy of the system in an empirical model. So every atom has a certain strain energy associated with the distance of its neighbors. So it basically looks at 4 neighbors and figures out, okay, you're that far away, you're that far away, you're at that kind of angle. Therefore, I accumulate a certain amount of strain energy. And you do that for everybody, and you don't double count. And then you let them sort of loose in the numerical sense, and they sort of figure out where they would like to sit and minimize the total energy of the system. Does that make sense?
Yes. It's just very complex. I mean, you have to probably do it several times.
Yeah, it's a conjugate gradient method. And it takes a while to converge, and you have to basically go through, 50 million degrees of freedom, and you got to find a methodology that you do that efficiently, because you don't want to have 50 million iterations.
So as I understand, first of all, you minimize the energy for each atom?
No, you do it at the same time. So you basically have an algorithm that loops over all the atoms, and for each atom it figures out, okay, I'm accumulating a certain amount of energy by being at a certain distance. And then you start wiggling the atoms around in a conjugate gradient method, and you figure out what is the direction in which I'm going to start to minimize the energy. And there's a sort of a trend. And that's numerically the most efficient thing is a conjugate gradient method. There's other less efficient methods. But that's a standard minimization.
Do you have to obey the second law of entropy?
Why would I violate it, I guess?
Yeah, and you would not violate it?
No, I don't think so. All right. So this presentation is overviewing what NEMO3D can do in silicon quantum wells and in silicon with individual impurities, and it gives you an overview of the importance of atomistic modeling of realistically scaled devices, and is really geared towards quantum computing approaches. So the title is Multimillion Atom Simulations of Quantum States and Transport in Realistically Extended Devices in Silicon for Quantum Computing. So clearly you've seen slides like this with industrial trends of devices getting ever smaller. And what I like to assert from my experience and from this graph here is that you have 3D spatial variations on a nanometer scale. It's no longer just planar scaling and these devices are large. You have potential variations on a nanometer scale. And you have really starting to look at new channel materials like germanium and 3,5 materials are reemerging again. So it's not standard silicon by itself alone. So then the questions and the challenges are that you have strain to deal with, you have quantization, you have crystal orientations, the atoms are countable. The question is, does granularity matter? Does size matter? New materials or new device? What are you really building, right? Is it a new device, or are you actually creating a new material that really doesn't exist like that, right? That connectivity of atoms and that spatial orientation, you can also interpret as a new material. And what I like to assert here is that it's important to deal with this at high bias in non-equilibrium. You got to do this in quantum mechanics, and you have to do this in an atomistic representation where you have band-to-band coupling, you have non-parabolicity, you have valley splitting, you have local disorder, you have strain and orientation. Okay? And those things are all important, and your model needs to comprehend that a priori. Meaning, you don't stick the effect in afterwards, but you have a model that intrinsically understands these concepts. Right. So this is a slide you might have seen sometime this week already in some form. As we are making devices smaller and smaller, we go through a regime of diffusive to maybe ballistic transport and then quantum transport up down to the atomic domains, right? And traditionally, you might know about drift diffusion and Boltzmann transport. And I mentioned before, it wasn't completely clear, and some people still would dispute it, what's the right formalism to use at this domain of quantum transport in atomic dimensions. So physicists in general, they will write in these atomic dimensions, they will write down a Hamiltonian, and they will write down a partition function, and they will say, well, I'll deal in equilibrium. Okay, that's good. They do really solid work, and they might even perturb the system through self-energies, but they still treat it in equilibrium in general. Now, I'm an electrical engineer. I have contacts on my devices, and I want to shuttle electrons in and out of the system. Okay, so I fundamentally all the time work in non-equilibrium systems. Okay? And with the introduction to NEGF that you probably saw this week, it should be clear to you that there's a mechanism to do that, and that is really this non-equilibrium green function formalism. And the beautiful thing is that you can rederive Boltzmann and drift diffusion out of that, and it's really a unified model. And it's so unified that you can look at it, many different devices. Nanowires, carbon nanotubes, molecular electronics, spintronics. The formalism as such doesn't change. Okay? It's a unique formalism that is very general and very applicable to a variety of systems. So you've seen earlier today this presentation here on the resonant tunneling diode. Here's a double barrier structure. You crank up the current. You crank up the voltage further, the resonance is under the sea of electrons, current drops, current increases again. Here's the experimental curves. They don't look quite like a Mickey Mouse device here. There's a bunch of experimental data on this curve in dots, and in the black line is actually the experiment before theory. The key questions in 1994 was really, can we make these devices with peak-to-value ratios better than 80? That was sort of the record at the time. We needed something more like 1,000. You needed to understand where the valley current comes from. And in 97, we were able to overlay experiment and theory. And really the key insights here is that we needed atomic device resolution of 2 to 5 nanometers. We needed to resolve it atomistically. We needed extended contacts with scattering, extended electrostatics, and we really built at the time the first nega simulator. So then stepping forward, we built this NEMO3D code where we said we want to do this in 3 dimensions. We don't want to just do it in gallium. We don't want to do it atomistically. We don't want to do infinitely periodic, so we take a local band structure approach. We don't need unstable bonds or chemistry, so we don't do ab initio. We do it parallel. we scale to 52 million atoms on a reasonable sized cluster. So we can do large problems. So what are the things we like to tackle? Here's a set of experiments out of a group around Mark Erickson in Wisconsin. They are building quantum dots, gated quantum dot-like structures, and measure something called valley splitting. And I'll talk about that. Here's another geometry. These are FinFETs that were built out of IMEC and measured in Delft. And people think they measured effects of single impurities in these devices. So I'm going to show you how you model those. Then there's another group, an experimental group, that looks at a very different set of silicon nanowires. These are actually rows of impurity delta-doped ions that are buried here in silicon, and they form semi-metallic nanowires. I'll talk about that. And then people are building quantum dots that are between such nanowires. So I'll talk about that. So these are extreme electronics in a sense, and they are all geared towards quantum computing devices. Here's sort of an overview. This is out of a programmatic chart where really we've been working on this for a couple of years now, since 2004. And really the goal is to relate NEMO3D type outputs to quantum computing applications. And this is my research group that did all this work pretty much. So, you know, as a professor, I get to sell this stuff and talk about it in public, but they do the real work. And here's now the sort of the overview of the presentation. I motivated a little bit the work. I gave you a little bit of an idea about the Nemo numerical engine. Now we're going to talk about valley splitting in silicon quantum wells and silicon quantum dots. I'll talk about single impurities in silicon, and then about dense impurities in silicon. Okay, those are the topics I like to cover. So here's this valley splitting issue in quantum wells. So this geometry that this group has identified is really gated quantum dots that are buried in silicon on top of a silicon germanium heterostructure. And silicon is a 6-fold degenerate semiconductor in the conduction band. And one of the fundamental issues in quantum computing is decoherence. And the more states you have close together in energy space, the more they're starting to, or the faster they will decohere, meaning they will lose their quantum mechanical information over time. So you like to separate those states as much as possible. And why would you do that in silicon? Well, silicon is the material of choice in the sense that there's industrial experience with it. And two, it actually, you can get a particular isotope that has no nuclear spin. And if there's no nuclear spin, the electrons will not couple to the nuclear spin and decohere via the nuclear spin interaction. So one way to eliminate some degeneracies is in this heterostructure here, where you have a 6-fold degenerate silicon. If you apply strain in the right direction, you can sort of shift those 4 away. So you only deal with 2 valleys anymore. Okay? So you're stuck with 2 valleys that are in principle degenerate. Now you have to understand how they interact with each other and how they create states. So you do that in a heterostructure like this. So this might be silicon germanium and silicon germanium. And you can shift away 4 of these valleys. But let's look a little bit more in detail. What is this valley splitting, or what does it mean? So if we look at a quantum box like this, like a particle in a box, we've calculated the most basic quantum mechanical problem in this particle in the box very simply, right? We can solve Schrödinger's equation that's written in here. And basically, you have a parabolic dispersion. You assume a parabolic dispersion like this. And if you do that, you find that your ground state is at pi over L. So you go into this dispersion here. And you have 2 states, right? You have a forward propagating and a reverse propagating state, right? An e to the ikx and an e to the minus ikx, or z. So you have 2 propagating states, and you combine them into one bound state, right? Because they interfere with each other, and they basically form a bound state. So that's all fine and dandy. So what you notice that the eigenenergy scales as 1 over L square, where L is the width of this well. So the smaller you make it, the higher the energy is the square of that. And so what you expect out of this, and what you should remember, is that you have state quantization, you have 2 counter-propagating states forming 1 bound state, and the energy is separated by 1 over L squared. Okay? So now silicon is a little bit more complicated, right? Silicon has really, along one axis, 2 equivalent values. Okay? So there's this guy here is not sitting at the gamma point here in the middle of the Brillouin zone, but it's sitting at X. And there's an equivalent one just like it on the other side. So if you now have a man-made system of a particle in a box of length L, what you have is 2 valleys, and you find 4 propagating states like this, right? There's 2 here, and then there's 2 on the other side in the other valley, okay? And those will form 2 bound states, and they will share an envelope that we love and like that is determined by really K1 and K2, by the distance between them from the minimum to this discretization point. But there's something more. There is fast oscillations that are inside of this that are determined by the minimum point here of K minimum at this X point. And then there's another one at minus Km. All right. So that means you have 2 states, and actually they split through their interaction. And once they split, they have this envelope, as I said here, that's determined by K1, 2, which is if we say we have a quantum well that is of length n times the lattice constant. So our L is n times the lattice constant. So the K is determined by A over NA, so 1 over N. But this minimum point here, these rapid oscillations are actually on the length scale of A, which means they depend on atomic overlaps at the edges. So here's your wave function like this, and at the edge, any details you modify at the quantum well of the edge are going to influence you very strongly, versus the confinement is relatively weakly dependent on the details. So that's the indication that whatever you do on your heterostructure and your bound in your confinement is going to be important. All right. So here are some of the first calculations we did with this valley splitting. So here's your quantum well like this. And the question is, what if you make this quantum well thicker and thicker, and you plot this valley splitting? And what you get is a rapidly oscillating function. This is on a log scale, right? So it's actually very strongly dependent on the length of this quantum well. And you can actually show analytically that this decay here roughly decays as 1 over L cubed, not the 1 over L square that you saw earlier. And from an experimental point of view, you might be interested in seeing actually a quantum well under bias, not just flat. So now you can say, okay, I'm going to make these different quantum wells under a certain bias. These oscillations start to go away for the longer quantum wells for different electric fields. So same curve, but now I'm starting to turn up the electric field in here, and these oscillations seem to go away. So now I can take this graph here, and instead of slicing it along monolayers, I can slice it along electric field. That's what I'm going to do in my next graph. And what you see is that the valley splitting, they all seem to fall on top of each other for high electric fields like this. So without electric fields, they are all very different for different lengths, right? And rather rapidly varying. But at the end, they all fall on top of each other. Why is that? Because at some point in the electric field, all these states are sitting in a triangular notch. And it doesn't matter how long you make that quantum well, because they never see the left end. Okay? So the key element of the first insight we had in about 2004 is that the device details, the structure, the materials, and the local fields determine this valley splitting. And you determine it through a calculation where you don't use that as a fitting parameter. It comes out. Okay? which was at that time novel. Most people actually used valley splitting as a fitting parameter to get the right result. All right. So we thought, well, this is cool, right? And we thought we had this all well understood. So in a sense, what you have here, so you have these two parabolas like this in silicon, and they interact with each other because there's 4 states, and then these 4 states form 2 bound states that have a dispersion, and they're split, and everything is golden, right? We understood everything, except for these dang experimentalists. They actually measure the stuff, and they find that, well, you guys are completely wrong. You're off by almost 2 orders of magnitude, meaning we over-predicted the valley splitting by 2 orders of magnitude. And we're like, that's not nice. So the question is, why is the experimental valley splitting so much smaller? And we started to get an idea that that has to do with the non-ideal structure of the thing they actually built. So instead of being a perfectly flat quantum well, they grew the silicon on top of silicon germanium that is actually tilted at a 2-degree angle, because they can get better growth at that 2-degree tilt angle. And then some strange things happen. There's these ridges, right, because it's at an angle, and there's a rough ridge and a straight ridge, and a rough ridge and a straight ridge, and a rough ridge and a straight edge, which is kind of funky, but it's very, very clean. They know about this, right? And we're like, okay, so there's something that is breaking symmetry, and this thing is actually at an angle. So we thought about that and started to model it. So we took a bigger unit cell instead of just a sliver like this. We took a bigger unit cell, slanted it at 2 degrees, and in a sense you can plot these 2 valleys like this now in sort of 2D zones like this, and they're tilted with each other. Okay? So now they overlap. Sort of, here's a projection of 2 parabolas like this. I'm plotting the same projection. They overlap, and they show a tiny valley splitting here at this gamma point. And unfortunately, it's completely irrelevant, because all the electrons actually sit below here at this energy, and they're degenerate. So in an ideal slanted structure at 2 degrees, valley splitting is 0, which would be the wrong answer from the experiment. Okay? So it only forms this meaningless mini-gap here. So valley splitting is really 0, and the question is, we need something else. In the experiment, something else is going on that is splitting these valleys. So they actually do that with a magnetic field where they couple these things here. So here are these mini bands here, and you can again form 2 pairs of 2 counterpropagating states, but you need something that couples them. So you can do that with a heterostructure, or you can do that with a magnetic field. In the experiment, they actually did that with a magnetic field. So, okay, we put in magnetic fields into NEMO3D. That was one of the first reasons we needed it. And so we predict this, and it looks like a linear curve, like what the experiment is, but unfortunately, a factor of 10 or so too small. Okay? So, at first we were 2 orders of magnitude too large, now we are an order of magnitude too low. So, no good. And the question now is, how can we reconcile this? So here's a flat quantum well, too large, a tilted quantum well, too low. It doesn't match experiment. So there's something else, right? So here's this tilted quantum well, and we can do a couple of things, right? Number one, we can say, well, these steps are not perfect steps. They're actually rugged. Okay? Also, surrounding the silicon is really silicon germanium. Okay? So let's look at that silicon germanium a little bit more carefully. I'm going to shock the cameraman. But so what you see here is a 25% germanium in silicon, right? It's an alloy. My friends, alloys are not ordered. Okay? What you think might be a nice, beautiful material is a Swiss cheese that is disordered. Okay? That means that interface, even if you made it as beautiful as you could, is going to be rugged. It's not a smooth material. It's not just material A and then material B, but there is silicon germanium. And it's disordered. So it should make a difference. All right, so let's figure out what the step order does at the atomic scale and what the alloy disorder does at the atomic scale. All right, so here's one experiment that I told you about. We take a quantum well, make it perfectly slanted at 2 degrees, and have an infinite wall, no silicon germanium. That's a 1.2 million atom electronic structure calculation. It gives us this result. No good. Factor of 10 too low. Now if we include rough steps in this kind of thing, so we make the steps actually rough, but still an infinite wall around it. We actually raise the valley splitting up by roughly an order of magnitude, and obviously there's fluctuations, right? Because there's noise on the system, so there's an error margin on our calculation. All right, the next thing we can do is actually take the structure like that and make it perfectly slanted, but put real silicon germanium around it. Really put the disordered material around it. It raises the valley splitting up as well. And there's noise on it because it's disordered. Okay? Guess what? If we put this all together, we actually perfectly overlap the experiment. You might call this fortuitous. That's fine. But it really shows that the atomic detail of the interface and of the interface material actually makes a difference on this particular set of experimental data. And that we can get very close to the experimental data. All right, going back to then the question, what happens if you don't have a slanted well, but you also have a real buffer around it that is finite in size? Actually there, it also raises the valley splitting up a little bit. So enhancing against the insight that if you look at valley splitting that is determined by a detailed phase from one atom to the next, what you do on the interface is of critical importance. Okay? All right. So here I've shown you sort of now the conclusion slide on that segment where really in valley splitting we have 4 states interacting with each other. There's 2 K numbers that are important. One is determining the envelope, that is the size of the quantum box. But the rapid oscillations at the momentum point here are really on an atomic scale, and they depend on the atomic overlap. And really sensitivity to atomic details is important, and we have sort of a critical understanding in that. We have some analytical expressions you can look up in in these papers, and analytical expressions for finite barriers. So there's a whole slew of papers that goes with that. Yeah?
The propagating state, there are 4 propagating states, but in the bound state is 2.
Right.
Means the degeneracy.
No, they don't need to be degenerate. In fact, they split because they interact. And that's that valley splitting. Okay, so that's sort of the insight we had on silicon quantum wells. Now I'm going to start looking at single impurities in silicon. Oh, sorry. Backtrack. Now I'm going to look at silicon quantum dots that are inside silicon germanium. So there's a group actually at Purdue around Professor Rokinson that is interested in embedding silicon quantum dots in a silicon germanium matrix to contain electrons in these quantum dots and use them for quantum processing. And just like what we did in the 1D calculations, what we can do is we can change the width of the dot. Oh, sorry, this is the height, vary LZ, the height of the dot, and keep a dot at 20 by 25 nanometers. We can track the valley splitting as a function of this dot height. And since we have statistical variations in the silicon germanium, there's always some error bars on these calculations. So let's look at that in more detail. Then the question is, of course, from the design perspective, well, it seems like uncontrollable, right? Where would you like to be to sort of have a better control of that valley split? And the quantum dot height can actually be pretty well controlled because it's within an MBE on atomic scale. So you can choose a point, say, here around 10 milli-electron volt, where you feel close enough. I have a valley splitting that's of reasonable size. So here we looked at the statistical fluctuations, and we'll pick a point roughly here. And then we can say, if you pick that point and your quantum dots are defined by etching, then you have less control in the lateral dimensions, right? So you can ask yourself, if you have little control in the lateral dimensions, does the valley splitting change a lot? And it doesn't. There's some noise on it. And we can look at, say, this sample here and actually blow it up has a sort of Gaussian distribution, and it has some full width half max of 18 microelectron volts in a background of roughly 180 microelectron volts. So there's a little bit of spread due to just disorder in the system of the alloy around it. But so there's this disorder. Does it matter? It seems to. Can you handle it somehow? Can you think about it in a different way? So what you have is, you have a crystal and you have silicon and germanium in it, right? And they could be pretty much random. At least as a Gedanken experiment, what you can do is say, what if they were ordered? Would it matter? Right? Because if it were ordered, then we would have a very regular system and there shouldn't be these fluctuations. And then the next question is, would these results be roughly the same as the disordered ones? Would it be sort of in the middle somewhere? So we've done that. We've constructed a unit cell where you have a unit cell of silicon germanium with 25% germanium in it. You can have one case where you only have silicon germanium bonds. The germanium are not next to each other. Okay? And we can have another case where actually the germaniums are next to each other. They touch at some point. Okay? That's the two configurations you can come up with. All right. And if you do a calculation of what the valley splitting would be in this very much ordered system, you would get a valley splitting that would be very different. It wouldn't even be somewhere in the mean of the disordered system. It's actually a different valley splitting. So that's sort of pointing to that strain matters, that disorder matters. And if you had an analytical model that sort of smoothed the material out to be homogeneous, chances are you get the wrong answer. So the atomic details seem to matter. All right. Then there's an issue on how deep do the wave functions penetrate into the barriers. You can do that with a sort of an analytical expression. And that goes along, the wave function penetration into the barriers goes along with the valley splitting as a function of quantum well height. I'm going to drop over this. So the key message here in this is that, again, in the quantum dot system, disorder in the buffer material matters. The details matter. And if you had an ordered system, you actually would get a rather different result than a disordered system. And the disordered system has some spread to it, and we can analyze the spread. All right. That gets me to my next segment, which is, I think, really exciting, which is the effect of single impurities in silicon. Now, you might argue, who cares? Well, if you think about your nano devices getting rather small, then doping will be discrete. And then you should ask yourself, what do these dopants do? Right? So that's part of this original motivation of this work. This is actually a FinFET device built at IMEC. And they cooled the device down, and they measured the current flow as a function of gate voltage. And at low gate voltages, so before the device really turned on, they see these really sharp spikes in the IV characteristic. And they hypothesize that that is really tunneling through single impurities. Okay? So that is not what I'm going to describe in the next few slides. It's really, I think, something cool. It's really connecting 3 different continents, working together in all kinds of conference calls to weird times, between Delft, IMEC, Melbourne, and Purdue. And really, what they experimentally were able to do is measure these current spikes in a, say, conductance type plot as a function of various gate voltages. And if you're in this field, you would recognize that immediately as a Coulomb blockade diamond. Okay, and Coulomb blockade diamond are indicative of single electron charging effects. And so here is a Coulomb blockade diamond, and there's these streaks on the side that run away like this. And these streaks tell you something about some of the details of the structure that you're tunneling through. There can be two things. It could be effects of the leads, and it could be effects on the inside of the device, meaning the impurities. And in fact, these are excited states of these impurities. So you can probe, this Coulomb diamond can probe the ground state of the impurity and the excited states of the impurity. So if you can probe that, you actually have a metrology to possibly figure out what you have, what kind of impurity you have. And we coupled that with modeling results where we can place an impurity into a NEMO simulation domain at a certain distance away from an interface. And if there's low field, the impurity will be confined right at the impurity. But if you apply a voltage, the electron will sort of leak out and against this interface, and eventually it will be just an interface state that is sort of loosely bound to the impurity. So you can do that for different impurity depths and different fields. And with a correlation matrix sort of many numerical experiments together with the experimental data on multiple devices, we were able to figure some things out. We were able to say that these impurities are arsenic and not phosphor. And we were able to determine the depth of the impurity from the interface. And at the end, we had a very nice Nature Physics article that came out of that. So the key message really as the introduction here is that you can do metrology with multi-million atom simulations, and you have to have the excited states to do that. There's many methodologies that will give you ground states in electronic structure calculations. In fact, most of them do. They could not have delivered this because you need the excited states because they are part of the spectrum. They are part of your fingerprint, so to speak, right? This is a fingerprint of a particular impurity in a particular device. And the excited states are part of the fingerprinting. All right, so in detail what we've done is we took various impurities, placed them at certain distances, and could figure out this mapping. So the next thing, I'm going to do this in a very brief highlight, is we can think about using donors as mappings of wave functions. Wave functions are normally conceptual things, right? You can't measure a wave function, right? But if you actually thought about the following a Duncan experiment, when you have an impurity here in the center and it binds an electron to it, if you could have a slightly different silicon atom here, a silicon 29, then this silicon here will have a slightly different, it's a different isotope. It will have a different hyperfine interaction of the electron wave function with the nucleus. And there was actually some measurements in 1969 here at Purdue that proposed some of this and did ESR measurements on this hyperfine interaction, and they measured indirectly the wave function. What we're proposing here is to measure indirectly the wave function of such a system. So what you do is you can calculate these wave functions, you can calculate this hyperfine interaction tensor, and that is something you can possibly measure statistically and then step back and map the wave functions, which is kind of cool. And that was published a year ago in PRL. There's actually experimentalists now trying to hunt that down and trying to implement it, which is kind of cool. Once you have impurity states under control, you want to put them in electric fields, and you want to steer them from one quantum dot into the next, and you want to manipulate them. So that's a study we've done where we looked at the so-called G factor. That's the change of the electron eigenstate energy as a function of magnetic field and its dependence of the surrounding material. And we can do this for different materials in different crystal directions. And that's recently got published. And finally, we're getting to something. What would you do with some of these impurities? Could you string them together in rows and then maybe do quantum computing with it. So that's one of the quantum computing architectures. It's called coherent transport adiabatic passage, where you inject an electron on one end and you try to shuffle information from qubit information from one end to the other. And you want to do that such that the wave function is never non-zero here. So you'd like to get a coherent transmission from here to here without really traveling through there. And that is what the CTAP algorithm does. And we identify sort of a gate configuration that might enable that. So this is sort of a first example that with single impurity computing, you might be able to build a quantum computer. Okay, and that there's reasonable gate configurations that you could do it. The bad part is that you're strongly dependent on the exact positioning of these atoms. So what we now have to think about and have done so far is think about an adaptive gate tuning so you can actually find this so-called CTAP path. And that's being done sort of in collaboration with Sandia and Melbourne right now. So that's sort of a rapid overview of what we can do with single electronics in single impurities, where we can look at fingerprints of single impurities in actually FinFET traditional devices, and then having dopant devices like this. All right. So now I'm going to talk about a completely and differently radical device that's very different from whatever you normally think of. So here you have a atomic precision doping by an STM. So what you do is you have a hydrogen passivated surface in silicon, and you come along with an STM tip, and you actually take away some of these hydrogen atoms. Okay? And then you come in with phosphine, and the phosphine actually sits down on that depassivated surface. And it can't sit down where it's passivated with hydrogen. And then you can overgrow this again with silicon, and you start to bury the phosphine under the surface. And that sounds pretty crazy, but people actually do that. There's a group around Michelle Simmons that builds these things. And the cool thing is you can get impurities in there where 1 in 4 atoms is phosphine, or phosphor. That's incredibly highly doped. Okay. So then there's a bunch of questions that arise with that. Oh, okay, let me go back. So what they do is they cap it, then they etch down, bring some aluminum contacts, and they actually contact that sheet. Okay? And then they can start to measure current flow through such a sheet. And they can pattern these sheets, right? They can make big pads, then they can make a thin wire around it and then connect to a big pad. And they can actually measure current flow through these structures. And these wires are as thin as 2.3 nanometers. That's 4 atoms wide, 1 atom thick. Okay? If you talk about ultimate limit of nanoelectronics, that would be it. Okay? That's really small. And there's a bunch of questions that then arise, right? We want to understand the available experimental data. We want to guide them. We want to know, is this behaving like a metal, like a semi-metal? What would the conductance be? How sensitive are you to fluctuations in these devices? What is the effects of doping density, wire size, and orientation? And can you gate these things electrically? And what we use is this NEMO3D approach with real charge self-consistency. All right, so we're going to look at these big pads first. Okay, so forget about the wire. We're just going to look at these big pads. So if you have a big pad of these impurities that are in a sheet, you can think of this as sort of like a Coulombic well. Okay, there's a bunch of Coulomb potentials there. It's basically a Coulombic well. So you're going to confine electrons in this Coulombic well. Okay. So also, you may not have to compute this whole huge sheet. You can just take a unit cell and repeat it. Okay. And then you can make it large enough in the vertical direction, hopefully. So what would happen if you quantize silicon? So that's similar to what we've seen before. You have a 6-fold degenerate silicon. Now if you quantize it in, say, this vertical direction, what happens is that these gamma values, these X values here project to a gamma point, okay? And they split. That's called valley splitting, okay? In the previous case, in the beginning of the lecture, these other four, these blue and the red ones, were shifted away by strain. But now we don't have strain. They're actually in the picture, okay? So in a 2D projection, they just project into this 2D Brillouin zone like this. Now, that means if we compute a dispersion in this 2D Brillouin zone, we see two states at the gamma point, and they're split, just like what we expect. And then we see these X valley type things here. We call them delta valleys here in the 2D Brillouin zone. And we see a whole bunch of excited states, and here we see a Fermi level up here. So there's a bunch of electrons that are occupying these states, and zero actually here is the bulk silicon. Okay? So, yeah?
The two gamma band state is due to string.
No, it's due to valley splitting. It's band-to-band interaction, just like in a single quantum well. So you have a quantum well where you confine electrons and say silicon bulk is here at 0 eV. And then you have a negative quantum well and you confine electrons in there. And then the bound states will sit under 0 energy. Okay? So that's what this graph is. You have a bunch of states that sit under 0, and these are basically, this is the evidence in a sense that this is a semi-metal. That sheet of highly dense impurities acts like a semi-metal. So at the Fermi level, you have a ton of states that can conduct, just like a metal. And you do that in the middle of a semiconductor. Okay? So you create a local metal that has so much electrons in it that it behaves like a metal in an atomically thin sheet, which is a kind of cool thing if you can start to control that. All right. Oops. So the way we compute this, we solve NEMO3D Schrödinger equation, we impose a Fermi-Dirac distribution of states, calculate the Poisson, calculate an LDA potential, feed that back onto Schrödinger, and keep going, and we do this in a unit cell like that. There's other people that have done similar things. They've done this in pseudopotential calculation and other effective mass-like calculations, and they get similar energies to us in for the gamma point and the delta 1 points. So we compare well. Now you might say, so why do you do that in your way, and why don't you just adopt theirs? Well, in our tight binding way, we can do huge structures. We can start to look at disordered system. We can look at conductance, which these DFT calculations can't do. Okay? But we want to calibrate ourselves against those kind of calculations. All right. So now let's look at some of these nanowires here. So we looked at the pads, and now let's look at the nanowire. And what they measure experimentally is actually a conductance through this structure that actually goes down and goes back up as a function of gate voltage. So let's think about modeling some of that. So let's take a sliver of such a device, and it might look like this, right? So there's a cross section and there's a little wire, and we make a supercell calculation. We assume that this thing is infinitely long. Okay? But we make the cross section wide enough that we don't feel this edge. All right. So then we model, this is our unit cell. It has 2 phosphor atoms in it, but many, many silicon atoms in the cross section here. And then we repeat it in this direction, in particular in this 110 crystal direction, which is the one the experimentalists have done the growth in. All right. So what happens if you transform silicon into a nanowire? So this projection you've seen from 3D into 2D Brillouin zone. And now you can quantize it one more time into a 1D Brillouin zone. And what happens is that you had 2 gamma points here and you have blue here again. They will quantize and get you 4 gamma point-like states and 1 delta point-like state. Okay? And indeed, if we do this in the quantization like this, we get 4 states here and 1 delta. Okay, so it makes sense, comes out to be right. And again, 0 is bulk silicon, so this actually acts like a wire that is semi-metallic. If we do a slightly different orientation of a wire, we rotate these guys around, they project down like this, 2 in the middle. But now if we quantize in this direction, we actually have 2 delta values and 2 gamma values like this. And the projection will look like this, 2 and 2. So it will matter in which direction you run that wire, whether you run it in 100 or you run it in 110. Okay? Just from the underlying silicon band structure. Right? So here's this comparison, 4 and 1 and 2 plus 2. Interestingly enough, the conductance is roughly the same. It's 6. There's 6 bands that run through the Fermi level. Yeah?
So why is the Fermi level using the conduction band rather than matter?
What the boundary condition is that we say we have 2 impurities and therefore we have 2 free electrons. So we force the system to have 2 electrons. So it's charge neutral. So for it to be charge neutral, these bands need to flow down to minus 200 or so, versus 0 is always the reference of bulk silicon, and the Fermi level needs to occupy to there. Okay, so now you can compare 3 different crystal directions, and if you actually did this in 111, it would be still looking different. You can count the states at the Fermi level, and you can conclude that you basically, the conductance doesn't change, but the details of the band structure changes. Okay? Now you can ask yourself, what happens if you make that wire wider and wider? So you will pack in more and more states, just like a normal top-down nanowire. We pack in more and more states. You get more and more conductance, and it goes not necessarily linear. You have 6, roughly 6, and then 17, and then roughly 24 states. Then you can ask yourself, what does doping dependence matter? So you can take an ideal unit cell like this and basically make the unit cell bigger and bigger, relatively reducing the doping. And if you do that, you basically see that your bands are getting flatter and flatter, meaning you're less likely or not as easily transporting charge through the system, and indeed your number of conducting channels goes down, which is kind of intuitive. If you take out more and more doping, you get less and less metallic. Okay? And then the last thing we did here is if you have a pretty shallow doping already or a little doping, and you play with the placement of the doping, so you have them equally spaced and then make them smaller and smaller spaced in this unit cell, what you have is even less and less conduction because you have more and more localization of charge. So here the charge is still distributed. At the end, you really build quantum dots that are determined by these impurities, similar to what we saw in the FinFET. All right, so we kind of have a handle on these wires in terms of raw conductance. But the question now is, can you modulate them like this? Can you think about modulating the charge? So let's look at that. There's a local band structure we have computed, right? We referenced the bulk conduction band edge, and we have a Fermi level and then a ground state, right? And now we're connecting that to a source along this direction. This wire is connected to some source on the left and the right, and its energies are such that we normalize to the silicon bulk edge. The Fermi level is slightly different, and the bands are slightly different. And in equilibrium, of course, this stuff has to align, meaning the Fermi level needs to be flat, so you build in a potential. Okay? So you have a big contact that has a certain Fermi level and band edges, and you have a central region that has a Fermi level and band edges, and they're going to align if this is to remain charge neutral. And then you can ask yourself, can you modulate this barrier height? Right? Because that would modulate that new transistor or that new current flow. And what we do is a numerical experiment where we force into the system a charge of just 0.8 and 1.5 or 2 and higher, okay? Where we violate charge neutrality. So this is here this numerical experiment where we ramp from 0.8 electrons to 2 electrons, and we see how the band edge actually moves, and the dispersion moves, and the charge moves, and the conductance moves. And look, the conductance is low at first, and it goes higher. Okay? So you can think about this being modulating the structure. And what you also have is really that the charge is not just sitting on the impurities, it actually is leaking out into the silicon. And you can start to look at that in this charge ellipsoid, and you see sort of the charge breathing out and in as a function of charge density. And if we do these calculations, we can roughly overlap the experiment of conductance in a system like that, which is a really cool thing in that, I mean, these are, number one, very hard experiments. And number two, these are really hard calculations to do. And that we even get reasonably close is a pretty exciting thing that tells us on the modeling side we're doing things right, and also on the experiment we're starting to understand things. So as numerical experiments, as Gedanken experiments, we can do variations of against the direction dependence, or the dispersion seems to be strongly dependent on it, but the conductance is actually weak, which is kind of surprising at first, right? So you travel, it looks like the dispersion is very different, but the conductance at the Fermi level is the same. And we could study doping and width and configurations and find that the dispersion and the conductance are strong functions of the width and the doping. And we still need to understand this charge control a little bit better and the electrostatic potential. And if you're curious about these kind of crazy looking band structures, there's actually a tool on NanoHub called Band Structure Lab that actually allows you to look at that. You can carve out a piece of silicon. It's not an impurity that's confining the electrons, but it's a particle in a box, and you find very, very similar dispersions. Okay? So it's a matter of quantizing silicon in that. So I'm going to go rapidly over this, and the final item here is now people are in the same research group, they're starting to couple these wires and build little quantum dots in the middle, and they start to tunnel through that. And so this is now the conclusion of my slides, really. We are doing multi-million atom simulations. We have enabled numerical experiments that you couldn't do otherwise, neither experimentally or theoretically, right? You have like a microscope on doing things. You can do this for realistically extended devices, not Mickey Mouse structures. We can quantitatively explain experiments with valley splitting in quantum dots, single impurities. We're not quite there yet on the dense impurity channels. And the challenges are that strain and electronics are far-reaching into the crystal. Disorder matters. Valley splitting is interface dominated, and scattering and impurity scattering in dense silicon phosphor systems does not seem to change the performance. Meaning, these highly dense impurity systems, you can mess with them, but conductance is still very good. It's like a semi-metal, which is really solid in terms of conductance, which is very nice. So that sort of concludes my NEMO3D application section. Yeah?
So for the SIP nanowire systems,
yeah.
Do you think the service state, the service quality will be important here?
Sorry, can you repeat?
For those nanowire systems,
yeah.
What do you think the surface states or the surface quality of the nanowires?
There are no surface states.
Right.
They're deeply buried. Like here, this is sort of a photograph in the production process. At the end, the phosphor is buried like 10, 20, 30 nanometers under the surface. So this is a buried metallic wire. It doesn't have surfaces.
Oh. How about the interfaces?
Well, it's there's almost no strain. This phosphor fits almost perfectly in silicon, so it doesn't even cause strain. There's no broken bonds. It's a perfect crystal. Okay. Any other questions? Yeah.
You talked about valley splitting, and that was due to strain at the beginning, and then later on, just now, you're talking about valley splitting due to confinement.
Not quite. Even in the first case, it was due to confinement because two valleys were coupled due to confinement. The other four were pushed away by strain, but it left two, and those two are coupled by confinement. Yes. So I have that Ushida structure on that slide, which is like 5 atoms thick, quantum well. There will be a huge valley splitting in there just due to confinement. Right?